Hi, pre-calculus friends. We're in Chapter 6 looking at Section 6.1, Angles and Radian Measures. So our vocabulary starts off with the concept of a radian. And the radian is this idea of thinking about the measure of an angle, kind of in the unit circle, but we think about the portion or the arc that is intercepted by the angle. I know I'm saying a lot, so watch this, guys. If this is the angle, whatever that angle is, the radian is this arc here. Let me make that just a bit thinner. The angle is going to be whatever that radian measure is right here, this length right here. So what am I talking about? Let's think about it a little bit. Do you remember how to find the circumference of a circle? The circumference of the circle is 2 times pi times r. So in this case, the circumference of the unit circle is going to be 2 pi, right? Because r is 1. And so if I go around the whole thing, that's 2 pi. So if I were to tell you or to consider the angle 360 degrees, 360 degrees is equivalent to 2 pi. This would be the radian measure. Nope, sorry about that. This would be the degree measure, and the 2 pi would be the radian measure. Okay, and so oftentimes you'll see radians that are not in pi form. It'll be like this 2 pi would be 6.28 radians, but that's going to be the entire circle. So if I wanted to kind of ratchet it down a little bit, I could divide both sides by 2, and you could see that 180 degrees is equal to 1 pi radian. So if I went from here to here, that's only 1 pi. 180 degree angle measure would be 1 pi in terms of radians. If I continue with this idea, recognizing that I'm dealing with radians over here, and I wanted to know what 1 radian was equal to, I divide both sides by pi, and I get that 1 radian is equal to, you see it here, 180 degrees divided by pi, right? Okay, similarly, let me scooch that up a little bit. Similarly, if I wanted to figure out what 1 degree measure was, if I had 180 degrees, right, and I know that that's equal to pi radians, if I wanted to figure out what 1 degree was equal to, I divide both sides by 180, and you guessed it, I get that 1 degree is equal to pi over 180 radians. Okay, so we're going to get used to using radians and using degrees, but right now that's what I want you to know about a radian. A radian is the measure of the arc that is created by an angle within the unit circle. So it's the measure of that arc, the circular arc length. All right, so with that in mind, let's talk a little bit more about circular arc lengths and different parts of a circle that we need to keep in mind. So when you're dealing with a circle, in this section particularly, we'll be thinking a lot about a circle. When we're dealing with a circle, we know that the angle that is at the center of the circle that has its rays or sides that are radiuses of the circle, we know that that's called a central angle. So this guy here, this theta, would be referred to as a central angle. Let's highlight that in purple if I can. Let me just squiggle that in there. And we'll refer to this as the central angle. The circular arc, let me use another color. The circular arc is going to be the arc that is intercepted by that, and I'll make that a little bit thicker. So that's the circular arc, that's this guy here. And we can talk about the length of that arc. And then finally, when we talk about the actual sector, and I'll leave that in a yellowish color, the sector is the entire thing. So oftentimes we'll talk about the area of the sector. So how I remember this is that the sector is kind of like a slice of pizza. So if the sector is a slice of pizza, the circular arc is the crust of a slice of pizza. And so hopefully that makes sense. And of course the central angle would be that nice angle that the pointy part of your pizza makes. Okay, so with that, let's go ahead and move on to a few examples. So let's remember a couple things that we learned in the last section. Well, let's bring it to light. We know that if we have a radian, there is an equivalent degree measure, that's an IAN. There's an equivalent degree measure. So there is a way or a unit conversion factor that we will use when we go from radians to degrees. So when going from radians to degrees, what we want to do is multiply by 180 over pi. Okay, if I'm starting with radians and I want to go to degrees, this is the conversion factor that I'll use. But when I start with degrees and I want to move to radians, I'm going to use the reciprocal conversion factor. So I'm going to multiply by pi over 180. A little helpful tip is if you want to change your radians to degrees, you want to put your radians on the bottom. You're going to cancel out your radians and you'll be left with degrees. If you want to change your degrees to radians, you'll put your degrees on the bottom. All right, so with that in mind, we're going to change 330 degrees into radians. So it's degree to radian. I'm going to multiply by pi over 180 degrees. Notice that we were asked to leave it in terms of pi. That means we don't want to use an approximate value for pi. We want pi to stay in the equation. So I will multiply these two together, 330 pi over 180. And the degrees are going to cancel out, and I will be left with, well, I'm going to cancel out the 10 at the top and 10 at the bottom. Then I'm going to divide top and bottom by 3. So I end up with 11 pi over 6. So this 11 pi over 6 is the radian way of looking at 330 degrees. Let's look at this next example. So now I'm going from radians to degrees. So I start off with 2 pi over 3, and I'm going to multiply by, let's look up here, 180 degrees over pi, because I'm going from radians to degree. So when I multiply by that, my pi's cancel out. Cross-canceling when we multiply fractions, you guys remember that. Then I have 2 times 180 degrees divided by 3, and I don't like to do a whole lot of math if I can help, so I'm going to divide this 3 out before I multiply by 2. When I divide 3 into that, I get 60, so I get 2 times 60, which is 120 degrees. So 2 pi over 3 is equal to 120 degrees, and 330 degrees up here is equal to 11 pi over 6. We'll talk a little bit about how we can start to see some patterns here in the next example. So before even starting the next example, I want you to take a look at these two charts, and what you'll see is that you can see some kind of relationship. Let's zoom in here and let's look at just this section here. If you notice that pi over 6 is equal to 30 degrees, right? We started off talking about that pi was equal to 180 degrees in terms of radians, and you can see that pi over 2, half of pi would be 90 degrees. And you can also see that a sixth of pi would be 30 degrees. Well, you can kind of take that and work with it. If pi over 6 is 30 degrees, 2 times 30 is 60, and therefore 2 pi over 6 or pi over 3 is 60 degrees. Even 60 degrees being pi over 3 tells me that 2 pi over 3 would have to be 120 because it is double. So this circle gives us all of the references that we would need to think about things that are multiples of 30. Angles that are multiples of 30. And then when we think about angles that are multiples of 45, like 90 is, we already saw that 90 was pi over 2. Half of pi over 2 would be pi over 4. So 45 degrees is pi over 4. And you can kind of use that as a reference guide to find all other angles that are multiples of 45 on the unit circle in terms of radians. And then we have this handy chart down here. So let's get started thinking about this next problem. This problem asks us to calculate the cosine of 4 pi over 3. And if you're like most students, oftentimes because we're comfortable with degrees, we want to think about them in degrees. And I'm going to say for right now, let's go ahead and do that. So if I change this back to degrees, remember we just saw that pi over 3 is equal to 60 degrees. So if that's the case, 4 times that would be 240 degrees. So this is the same as calculating the cosine of 240 degrees. You can see that 240 degrees is down here. When I think about that, I'm thinking of what's the reference angle. Remember, the reference angle is the angle that terminal side makes with the x-axis, and that's a 60-degree angle. So if I know the cosine of 60 degrees, and then I think about its location in the third quadrant, I've got the answer to this problem. I know that the cosine in the third quadrant is negative, so I know my answer will be negative. And the cosine of 60 degrees if you remember from a while ago, is going to be 1/2. You can use your calculator if you needed to kind of have a refresher, but remember the chart we had? This is one of those things you want to memorize. If this is something you need to talk to me about, we can do that. So your answer is a -1/2. I know this is a lot to think about and a lot to hold on to, but try to just play around with it in your mind. Try to test yourself and see if you can kind of come up with this on your own. I guarantee you it will pay dividends. Okay, let's look at number 3. So number 3, it says, given a central angle of 128 degrees, we are supposed to find the length of the intercepted arc. So let's assume that we have this thing that's 128 degrees. Let's assume that our circle has a radius of 5 centimeters. The intercepted arc would be this yellow arc that I'm highlighting here. We need to find this length. In order to do so, we're going to use radians, and you'll see why in, whoa, just a minute. Let me make this nice and large so we have space. All right, so if I look at this and I think about the unit circle, and let me use a different color so I can have some differentiation. The unit circle would be somewhere right about here, right? And we know that this would be 1, and this arc here would also be the length of the radian. It would be the radian measure of 128 degrees. So let's say I say that radian measure is theta, right? Let's say I use the Greek letter theta to represent that radian measure. Here's the relationship that I see. Radian to radius is equal to arc length to radius. You guys see that? So here's my setup. Theta over 1 is equal to, let me change my color here, 5 over this length here. Oh, no, not true. This length here, let me get it right, over 5. Let me talk about that again because I almost got myself confused. So the arc length, which in this case is the radian measure, and 1, which is the radius of the unit circle, is equal to the arc length and the radius of the larger circle. They are proportional. And I hope you can kind of sense that proportionality from some of the things that you've done in geometry, but yes, they are proportional. And this is going to work out. Remember that this theta, by the way, is indeed in radians. So watch how we're going to solve for L, which is what we're looking for if we scooch all the way back up here and we see what they're asking. It says find the length of its intercepted arc in the circle with this given information. So if I'm going to solve for L, I'm going to cross multiply, and I realize that L is equal to 5 times theta. And so this theta, again, it should be in radians. I only have it in degrees, so I need to change that. So that length is equal to 5 times 128 degrees, I'm changing it to radians, times pi over 180. And so with a little bit of calculation, I'm going to get 5 times. I'm going to divide both the top and bottom by, let's say 4, and I get 32 pi over 45. And with a calculator, because they did ask us to round it to the nearest tenth, we see that this is going to be approximately 11.17 something, and to the nearest tenth is going to be 11.2. So this is the length of L is approximately 11.2 centimeters. Remember what we just did? We use the comparison, we use the proportion when we thought about the radian with reference to the radius of a unit circle, and then this arc with reference to the radius of the circle. We set it up, we solved it, we got that L is equal to 5 times theta, where theta is a radian measure, and we did the thing and we got the length. So what we can say from what we just did, because we're going to use it again, is that to find the arc length, I like to use L. The text uses the letter S, but to find that L, that arc length of a circle, it's going to be equal to the radius of the circle. That R stands for radius and not radian. The radius of the circle times theta, which is the angle in radian. So you want to write that down. Of course, the text uses S. If you prefer that, you can do that as well, guys. Okay, so let's take a look at this next example. It says Winnipeg, Manitoba, Canada, and Dallas, Texas lie along the 97th west longitudinal line. So we're kind of looking at a cross section of the earth, and we see that they're on the same line. The latitude of Winnipeg is at 50 degrees north, and the latitude of Dallas is 33 degrees north, and so we have it here. The radius of the Earth is about 3,960 miles. Find the approximate distance between the two cities. And so you can see we have a setup just like we had last time. So what we should probably do, we're trying to find the approximate distance between them. So what we're trying to find, honestly, is this distance right here. And so if we want to find this distance here, the distance between the two cities, what we need to find is this angle right here, because that's going to be the central angle that we need. So 50 minus 33 is going to be 17. So the angle that we're concerned about is 17 degrees. Are you guys with me? And so what we're going to do is just use this to find this L, this distance here between Winnipeg and Dallas. We are going to take that value L, which we're looking for, so we're going to put L down there, and multiply it by the radius, which is 3,960 miles, times theta, which is not 17, but it is 17 degrees turned into radians. So we're going to write 17 times pi over 360 degrees. And not 360. I keep doing that, by the way, over 180 degrees. Remember, pi is equal to 180. 2 pi is equal to 360. So I am going to definitely use a calculator on this one, because that 17 and that 180, nothing good is happening. I'm not reducing anything. So I'm going to just take a quick break, go get my calculator. And with my calculator, I get this value of 1,174.96 miles, something like that. And so we'll just say 1,175 miles between the two cities according to our approximate value here. This next problem asks us to consider the area of a sector, and we are given a formula that is pretty simple to derive. I won't spend the time doing it here. To derive, to find the area of the sector given an angle measure in radians. So it would be 1/2 r squared times theta. And if you want to check that out in your text, it's on pages 346 to 347. It's a neat little derivation. So the area of a sector, and you remember what a sector is that slice of pizza. An area of a sector is given as 1/2 the radius squared times theta, times that central angle in radians. And so they asked us to find the area of a sector if the central angle is 5 pi over 6 radians, and the radius of the circle is 16 centimeters. So we can do that. So the area of the sector, I like to put this little slice of pie down there, is equal to 1/2 16 squared times 5 pi over 6. And since this is already in radians, we don't have to do the thing that we did before, which was translating it. So 16 squared is going to be 256, but then I'm going to take that 256 and I'm going to divide it by by 2 rather. So I end up with 128 times 5 pi over 6. And since I say round it to the nearest tenth, I'm going to take this opportunity to grab my calculator and actually calculate it using a little bit of technical help. And with that technical help, I get 335.1 centimeters squared, because I think we were talking about centimeters earlier here. And so that's example 5. Which brings us to our final example. Example 6 is using the concept that we have at most of the chapters, where we look at a problem from the beginning of the chapter. And so let's go ahead and do that. Junjira Putiwuthagal Gul owns a business in Chiang Mai, Thailand that makes ornate umbrellas and fans. Miss Putiwuthagal has an order for 3 dozen umbrellas having a diameter of 2 meters, and the bamboo slats that support each circular umbrella are divided into 8 sections or sectors. Each section will be covered with a different color fabric. How much fabric of each color will Miss Putiwuthagal need to complete the order? And so really what this comes down to is, what's the area of this sector? That's what it is. We talked about that. We had a little formula before. We know the area is equal to 1/2 radius squared times theta. And so that's the information we need, and we should be able to do this rather quickly. So the area of one of these little sectors is going to be 1/2, and what's the radius again? The diameter is given as 2 meters, therefore the radius is 1. So 1/2 1 squared times theta. So remember, theta needs to be in radians. Can you quickly tell me what the radian measure would be here? You remember that all the way around is 360 pi, all the way around is 2 pi, halfway around is pi, half of that is pi over 2, and half of that is pi over 4. Hopefully you got that before I said it. So pi over 4 is going to be that theta measure there, that radian degree of theta. And so the area is going to be pi over 8. You guys see that? Because I'm going to multiply all this together, I get pi over 8. What are we dealing with? Pi over 8 meters squared, since our information was in meters. Do we need to do it in decimals? Nah, let's just leave it like that. All right, guys, I'm hoping this made sense. Let me know if there's any questions. I look forward to talking to you soon. Please take care. Bye-bye.